Hello, I'm Dr. Kathleen Schmidt from Lawrence Livermore National Laboratory. Welcome to the Data Science Institute's virtual seminar series. With Lawrence Livermore being home to many challenging data sets, as well as some of the world's most advanced supercomputers, data science has become an essential discipline in the lab's key program areas. The DSI acts as a central hub for the lab's data science activities by fostering collaborations, promoting research, and engaging in outreach activities. Our DSI staff work in a variety of areas, including artificial intelligence, big data analytics, computer vision, machine learning, predictive modeling, statistical inference, and uncertainty quantification. The DSI hosts events like this seminar series to introduce new ideas and potential collaborators to the lab. We invite speakers from other institutions, both from the Bay Area and beyond, to share their innovative projects, approaches, and ideas with our data science community. We're pleased now to include a wider audience beyond the lab to engage with us through this series. You can read about past speakers on our website, data-science.llnl.gov, or email us at datascience@llnl.gov. Thank you, and enjoy the seminar.
Our speaker today is Dr. Brad Malin, who is a professor of Biomedical Informatics, Biostatistics and Computer Science at Vanderbilt University. He's the co-founder and co-director of two very impressive centers, the Center for Genetic Privacy and Identity in Community Settings, as well as the Health Data Science Center. And his interest in data science, as well as AI and computer science, makes him a really great fit for our seminar series and to collaborate with a lot of different people in our Data Science Institute. And today he'll be telling us about his work in AI and data privacy.
Thanks. So am I taking it from here?
Yeah, go ahead and take it away. And it looks like your slides are not up anymore, so we can go ahead and share those one more time.
I'll share again. All right, they should be up now, right?
Perfect, looks great.
All right, great. So I sincerely appreciate the introduction. That was one of the most concise and best introductions I've had. I wanted to talk about a couple things today. Some of you that saw me talk at a seminar a couple months ago got a little bit of the surface scratched on this topic. So I'm gonna delve in a little bit deeper into some of the issues and get into a little bit more of the quantitative aspects. But I wanted to set the stage for why I actually am working in this space and why others are starting to take notice. So this is really about questions around information sharing and getting access to individual level records for research purposes and possibly even for clinical or application and just general public surveillance. And so there's been a series of reports that have come out of various organizations, some of which are coming out of the national academies that are really promoting the sharing of information, mainly for the facilitation of things known as the learning health system. And there's a lot of different ways in which this type of sharing can occur. And I'm not necessarily going to go through all of these, but the motivation is really one of the trickiest parts about this. Because the incentive structures have to be set up in a manner that the holder of the information and the receiver of the data of the information get benefit out of it. And sometimes you'll see these incentive structures get out of whack, and that's what leads to a lack of information sharing. So there's also questions about when you actually share information, do you understand what happens to it? And I'm not really going to spend a lot of time talking about provenance, but I am going to point out that the notion of provenance and having an understanding of who's doing what with the data is going to be critical to ensuring infrastructure for information sharing. Okay, so what are we going to talk about today? So I want to talk about data, and I really want to talk about how it relates to AI frameworks and in the context of information sharing. And so the typical perspective on this is that you get a bunch of data, you throw it into some type of a learning framework, and then outspits some type of knowledge, right? Now, the question becomes, where do you do the processing? So the data we're going to assume is going to come from a holding organization, or what the Europeans would refer to as a controller, and then it's going to go into an environment where people are going to actually gain knowledge. Now, the question is, where is the AI framework? Typically, what people have always done is that they say, give me your data, and I'm going to learn from it, and I'm going to gain knowledge from it at the processor. All right, that's known as sending the data to the compute. The way things are starting to evolve is that we're starting to see a change in the paradigm, which is sending the compute to the data, where people are sending code in to the controller, or the controller is opening up some type of an API and allowing people to interact with the system. And then the learning will take place back at the controller, and then knowledge will only be provided back to the processor. And so that way, the controller has an understanding that the data has never really left their control. There's also a movement towards the notion of securing the entire pipeline here, and taking this entire AI framework and putting it behind an encrypted door, right? And so the way that people are starting to do things like this are taking advantage of secure enclaves. An example of this is Intel's SGX, or Software Guard Exchange framework, which, Software Guard extensions, where basically what you're doing is creating a trusted area within the RAM that you can create tamper resistant, such that you could compute over the data in any way you see fit, and nobody would ever see what was being computed over. So this is one of the ways in which information is starting to flow. Okay, so this works all well and good if you know what it is that you actually want to learn from the data, and you know what model you want to apply to the data from the outset. But you don't always know what it is that you want to do. And in reality, scientific investigation is more of a hypothesis generation, hypothesis refinement, iterate that over time type of situation. And so what you end up hearing from everybody is they really just scream, just give me the data. None of this complex infrastructure. This is going to take way too much time to really shore up and get perfected. And by the time we do this, the type of data that we're dealing with is going to change, and it's not going to be amenable to some type of environment that you've already established. So it's just, there's this push for really saying, well, it's not really saying, it's a push that's saying we're not comfortable with letting other people control our computation, and we're not comfortable with really relying upon the output of analyses without getting to see the data. So this creates an interesting trust dialectic. All right, now the reason why a lot of organizations, particularly in the healthcare domain, are very hesitant to let data go out the door is because of this guy. And if you're not familiar with this guy, this is William Weld. He was the governor of the state of Massachusetts, probably about 25 or so years ago. He was running for vice president, actually, about 8 years ago. And the reason why he's famous is because he was caught up in what has become known as the quasi-identifier conundrum. And what happened was that in the mid-90s, when Bill Clinton was in the White House and Hillary Clinton decided that she needed to take on an initiative, she decided that she was going to figure out how to support cost-effectiveness research in healthcare. And so in a bipartisan show of support, she and Newt Gingrich actually started going around to all the states and saying, what type of data do you need to do an analysis on, what is working and what's not working and what's equitable, right? So like what they were finding was that the different places were charging vastly different amounts for basically the same care. And it was unclear why it was happening. So policy researchers in many different states came up with these types of suggestions, which was they'd love to see the demographics on the patients, they'd love to know what happened to them, and they'd love to know how much it cost. And so this became what was called the hospital discharge databases in the US. By the time that the governor's case came about, which I'm about to show you, about 44 out of 50 states were making this type of data available. Now, the reason why the governor is important is that at the same time, around the same time, he was receiving an honorary degree from a college in Massachusetts, and he ended up collapsing, and nobody knew what happened to him during this session. What was known was that he was admitted to Massachusetts General Hospital, but nobody knew what happened to him, and it wasn't ever disclosed. So then an enterprising young MIT graduate student said, hey, I bet he's going to show up in the hospital discharge data. Now, that's interesting because he's going to show up in the discharge data, but then what she also demonstrated was that there's a lot of publicly available information out there that is really cheap to get your hands on. And the voter registration list for the city of Cambridge was available for 20 bucks. And she was able to cross-reference these two resources, find out that this was the only guy living in his 5-digit zip code with his birth date and his gender, and was admitted to Massachusetts General Hospital during that approximate time point. And this freaked people out once they heard about this, because the newspapers really started claiming that there was some really crazy hack that had taken place, that the computer scientist had cracked the secured environment that MGH was managing medical records at. And then really what was just shown was that you drop two relatively small data sets into Microsoft Excel, and you can just do a lookup within the two of them, and you would end up finding this guy's record. So people said, well, that's a freaky situation. And so they said, well, but is that a one-off? And so that led to a series of investigations that said, no, these really simple demographics are pretty distinguishing for the majority of the United States. And this is probably something that shouldn't be made readily accessible without some oversight. You shouldn't be able to get access to this without really agreeing to be a good Samaritan. So this investigation, this statistic, the 87% statistic that I'm showing here, this ended up becoming an artifact. It was written into the Federal Code of Regulation with respect to HIPAA, when HIPAA defined what de-identified data was going to be. They said, this is one of the reasons why you can't share data this way. That investigation really kind of set the world on fire. And so you can imagine that there are many different types of data that would be subject to re-identification, but one of the more clear illustrations of this, I believe, is with where we've headed with genomic data. And so what I'm showing here is just 500 genomic variants or single nucleotide polymorphisms, and you can see this is super high dimensional data, right? It does not take many pieces of this information to make an individual unique. Okay, that's an illustration of how privacy intrusions occur with respect to individual level records as the dimensionality gets higher. And then it was shown probably about a decade ago that you don't really need individual level records even to have an intrusion. And you'll see where I'm heading with this, because when you learn models off of data, the models themselves can be disclosive. And so an example of this is the way that data has been or was being made available by the NIH at the database of genotypes and phenotypes, where they were taking the results of large-scale genomic investigations, mostly genome-wide association studies, and they would make accessible the summary statistics of what did a particular population look like in that study, not individual level records, but just summary statistics with respect to each of the genomic variants. And so here what I'm showing you is that the variation with respect to certain alleles. And so you might see information with respect to the controls in a study, and you might also see information with respect to the cases. And so they were making this information available in the public domain. And then along came a forensic researcher that said, hey, this type of information actually shows up in other resources outside of your domain, where I can get an understanding of what the general reference population looks like, or the general population. And so there's data coming from the International HapMap program and 1,000 genomes. And they said, if I come forward with an individual's genome, I can provide an estimate of which population they appear to be closer to. And by doing so, if I can get a sufficient amount of variables in order to push somebody close enough to one area versus the other, then I'm going to have sufficient confidence to claim that they're over there. The NIH said, ha, 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 we don't believe you. And he said, well, give me some test cases. They gave him, I think, 67 test cases. And in 66 of those cases, he was able to correctly predict if an individual was within a study. In this situation, I'm showing, it was a controls but you can also envision a situation in which they end up in the cases. Imagine that one of those studies was focusing on sexually transmitted diseases, and you were able to prove that somebody was HIV positive or some other sexually transmitted disease. This would not be the type of disclosure that the NIH wants on their hand. And as an artifact of this, NIH ended up taking all of this data offline and throwing it behind a firewall, making it controlled access. The Wellcome Trust at the UK ended up doing the same thing, by the way. You think we would have learned? The Global Alliance for Genomics and Health a couple of years ago came forward with what's called the Beacon system, or the Beacon project, where they didn't even want to provide statistics on the alleles. They just wanted to give people the ability to query a resource and say, have you seen this variant or not? So basically binary queries. Sound like a great idea. Then Carlos Bustamante's group out at Stanford ended up showing that it was subject to almost the same type of attack that could have been used on the dbGaP database I showed before. And this led to also increased control with respect to beacons. Subsequent studies have shown that there's relationships between all sorts of variables, including everything potentially from facial structure and phenotypes that are inferable off of the genome to the point where you may be able to link the two concepts. Let's get that part. And then most recently, it's been shown that with really high dimensional data, when there's familial relationships, things can break down as well. So for instance, the genomic data has become so cheap to generate that you now have consumer-facing websites where people can take their data, throw it into an online environment and say, hey, I'm looking for kin, or I'm looking for an interpretation of what's going on in my genome. Can anybody help me? And this will be in the public domain. Well, the FBI figured out that this was possible, and then they started taking cold case DNA and probing these systems to try to figure out, can I find somebody who we're interested in, or can I find a relative? And that type of an investigation led to the first major breakthrough about 3 years ago, which was the discovery of relatives of the serial killer known as the Golden State Killer. And then they basically started asking people in the family saying, you know, we found you in this website, but you know, you're related to somebody who seems like they were a bit crazy in California in the 1970s and 80s. Do you know who that might have been? And that led them to this guy. It was then further shown by Jenny Verlich's group that there's so much of this data now that chances are that if you're a Caucasian with European descent, that you probably have no worse than a third or fourth cousin showing up in these databases now. Okay, so basically what I'm just showing you is an example of pick your favorite feature and it's going to distinguish you. I've shown you demographics, I've shown you DNA. I can show you many, many, many other studies in which these types of attacks have been perpetrated, both in the biomedical domain, as well as outside the biomedical domain. And so then I want to get a little two-faced on you, because what I just showed you is that the system can be penetrated to a certain degree. In other words, it shows that there is a potential for problems, but you really need to have the right type of circumstances. And not all systems are going to be made publicly accessible. And so you really have to think about this in terms of how much time, how much effort, how much incentive, how much money is somebody bringing to the table in order to run these types of attacks. Now, so what I've really shown you is that something's possible, but it's not necessarily what will happen under all circumstances. Okay, so as an example, this is something that we've taken to heart in the context of a big program that I help run the data protection model for, which is the NIH's All of Us research program, which is about a $2 billion earmark where we're in the midst of collecting data on about 1 million US residents, including their medical records, their biospecimens, and participant reported outcomes over a 10-year period. And we've started making this data public. But the public data that we've made is really only summary statistics, and they're only univariate summary statistics. So there's no easy way to chain link to get things together to run the type of membership detection attack I showed before. Now, but this is public. We've also created sandbox environments. And the first sandbox that we've created, which these are all based out on Google Cloud, is what we call the registered tier. And it requires you to prove your identity, and you need to come in from an institution that signs a data use agreement with the NIH. And what we've done is, as I'll show you in a bit, we've removed aspects of individuals that we know become pressure points for identifiability. Where we're moving towards early next year is going to be a controlled access environment, which is more heavily vetted with respect to the investigators, and it will provide much more detail with respect to the genomic information and more details around geographic area of residence. So we're heading in this direction. And how we got there was basically we went back to the same types of problems that we saw before in terms of looking at how re-identifications happen in practice and try to mitigate these risks by controlling the environment. So what do I mean by controlling the environment? So when you look at attacks that happen in the real world, you really have to understand where is the data coming from and where are the incentives being pushed around. So what I'm showing here is the type of attack that was run against the governor, how it would have played out in other states more recently. So what you see here is 5 different states with respect to how they make their voter registration lists available. And what you see is that the cost varies depending on the state, ranging from anywhere from like $30 in the state of Washington, it's actually $0 in the state of North Carolina, where you see that you'll get some of the interesting bits for committing an identification if you can get access to that data. But then it ranges out to states like Wisconsin, which is going to cost you almost $13,000, and you don't get any of the really interesting bits you needed for recognizing somebody in the database. Like you might get the geographic area, but you don't get the date of birth or their sex or their race. You just have an idea of where they live, which may not be sufficient to complete the attack. Okay, so there's variance here, and this is an artifact of the way that different states make different types of data available in different ways. And I bring this up because when you go back and you look at the studies that were done on re-identification, you almost always get this acknowledgement that says that, yeah, this is possible, but it really requires a lot of effort and manipulation with respect to the data and some luck. Okay, so there's an acknowledgement that says, yeah, the stars need to align. And so this is where I want to start getting more into the computational aspects of this problem, in that what we're looking at here is when you see papers or you see people talking about anonymity or identifiability issues, usually what they're talking about are aspects of, is the data unique? Is it replicable in another resource? And is it available in another resource? And if it is, then you claim that the system is going to be compromised. But in reality, it's more of a Bayesian situation, in that what that information tells you is the chance that somebody would be successful in compromising the system, given that they've committed the attack. But now you have to ask this question of, so what's the chance that they're actually going to commit the attack? And this is where deterrence theory comes into play. And we do all sorts of things to try to deter individuals from misusing data on human subjects. We might have you sign use agreements. We might make you pay for access for the data. We might bring you into a sandbox environment where we audit what you're doing with respect to a unique login and password. I could give you many examples, but you can envision, and you've probably been subject to various types of deterrence. So if you know anything about the privacy community, and even if you don't, there's a history of a development of various types of techniques to manipulate data to try to make it hard for somebody to commit an intrusion. And basically what they all do is they reduce the fidelity in the information, either by abstracting the data or injecting noise into the data before it goes out into the hands of somebody who's going to use it for an investigative purpose. And I think this is all well and good, but it really only is a little piece of what deterrence you can actually institute when trying to control the use of data. So that's a database control. But really what the way that we've started thinking about this is thinking about it from the perspective of two-party games, in that you have somebody who is trying to protect the information, somebody who may or may not misuse the information. And then what we've just shown you is one type of disincentive, but there's many other types of disincentives. But once you have them laid out, you can look at this from a strategic perspective, because the holder of that data gets to decide whether or not they're going to share the information. And they're going to do that based on what they think the recipient might do. And so once you know these strategies, you can actually set up routines in a procedural manner that will allow you to control the space. So this is actually a natural fit for game theoretic reasoning, which is really at its heart an artificial approach towards understanding human behavior. And so what we have is this publisher, right? They have a certain amount of benefit that they're going to receive from sharing data. Now, what that benefit is, it could be that they're getting paid for the data. It could be like if you are Vanderbilt, you might be receiving grant funding for the generation and the sharing of that data. You might be getting benefit through publishing the results in a high impact journal. Whatever it is, you can specify what that utility function is from the outset. What you don't know is what the risk is to sharing that information a priori. But what you can do is simulate various types of strategies that you would use to manipulate the data or manipulate the environment. And once you've done that, you can look at what a recipient might do. Okay, and you can simulate just about anything that they could do, even with private case out, they can look at all these different strategies from the perspective of the recipient. You can then say, so if they're acting rationally and reasonably, then what they should do is maximize their own utility function. And if they maximize their utility function, that's affiliated with a certain amount of risk that they will induce. And then I can just go back to the publisher and say, okay, well, this is the best option for the recipient under your particular strategy. So here's your utility, and now I know your risk. And you can play this out for every possible strategy that the publisher might be interested in considering, right? And so each of the strategies for the recipient may generate a different amount of risk depending on how the data gets shared, okay? And then you can play this out for all the strategies for the publisher and then choose the one that maximizes the overall benefit for them, right? And basically what you're doing is you're doing a dual optimization in that you're maximizing utility and minimizing risk. Okay, so how does this play out in practice? So to walk you through a little bit about how this might play out or how this works, we took 30,000 census records, and we were computing the average payoff per record, both to the defender or the publisher as well as the recipient or the attacker. And we calibrated this using a specific use case, where we assumed that the recipient, the generator of the data would get $1,200 benefit per record. And this was based on a NIH consortium that was generating electronic medical records data and genomic data. And we looked at how much grant dollars they were receiving as members of that network. And it averaged to $1,200 per record. Now, obviously, they're not being paid $1,200 per record. That money is being used to sponsor staff salaries, fringe benefits. But at the end of the day, you could argue that they're really being paid to generate the data. Okay, so then how could the intrusion pay out? We assumed that there would be a cost per violation on the order of around $300 per violation here. That was based on looking at how much an organization typically pays out as an artifact of an information breach. And then we looked at how much would an attacker have to pay in order to get the information that they need. And we found that on average, this was around $4 per record. Now, this is fundamentally what I've shown you a search problem, in that you can model the policies with respect to what their privacy and utility values are going to be. And then you can search the space because these policies, they have a natural order. You can search them using like an exhaustive search, like an inductive search using backwards induction. You can try and search using some type of an integer linear programming representation, or you could choose like a hill climbing strategy like genetic programming might offer. for what we're doing here, we used a very simple branch and bound approach. Okay, so what I showed you is like, what are the numbers going to be? How are we somewhat going to short search the space? But how do you actually play this out numerically? So what we did was we assumed that there would be several different potential results, right? And that initially say, so imagine that there's no attack that gets committed against the data. At this point, the publisher is going to get a payout that's proportional to the level of detail that they put in their data. Okay. Now, if there's no attack, that means that the attacker hasn't contributed anything. They haven't paid to play. They don't get any benefit. Their payout is zero, right? It's like going to Vegas and never playing. If the attack is run, then what we assume is that the publisher is going to get the payment for the publication of the data, but then there's going to be a potential for loss. And that loss is going to be proportional to the chance that the attacker is going to be successful and the amount of payout that they would receive as an artifact. And we assumed for the purposes of this version of the game that there was a zero-sum nature to it. So whatever the publisher paid out, the attacker was going to get. At the same time, if the attacker is going to get that payout, as I just said, with the zero-sum transfer. But remember, they're going to have to pay to play. So that's what this cost is going to be. That was the $4 that I showed you in the previous slide. Just as an example of why there's a natural order to these policies, this is just an example of what happens when you change the level of detail in the data. And this is just what happens when you have an age hierarchy. So you can see that there's a natural order to things here, right? So as a result, this is a tree with other types of features. They might also be a tree, but when you combine everything, it's a nice little partially ordered lattice. Okay, so I showed you the $4 claim. I would encourage you, if you've never done this, feel free to go to a company like Intellius or instantcheckmate.com and do a lookup for yourself or somebody that you know. And you're going to find out how easy it is to get the type of information that you need to identify somebody. It's not, this is a different route of identification than going and grabbing a voter registration database or some other state-sponsored public information. These are information brokers that basically gobble up data from wherever they can find it and then package it nicely and resell it for, it's not free, but it's not the most expensive data in the world. Okay, so now that you have that set up, you can start thinking about different types of games that might be played out in this space. So if you're familiar with HIPAA, you might be familiar with what's called safe harbor. If you're not, when you're sharing de-identified data in a healthcare situation, there's two different ways of doing so. One is what's called safe harbor, where it's the one that everybody says you've got to remove dates, you can't disclose geocodes on populations smaller than 20,000 people in size. It's what most institutional review boards are familiar with. So we said, so what happens if an organization wanted to share their data in accordance with safe harbor, the demographics that you would typically receive? How would that play out? And we wanted to compare the result to what would happen if you played this out under the two-party game theoretic framework that I just showed. And then we said, well, okay, maybe an organization is not going to try and maximize the amount of data that they throw out the door. They might say that the IRB is comfortable with a limit of what safe harbor tells you can do, but maybe you can share less information and maximize your benefit in that situation where they're comfortable with what you're doing, as opposed to telling them, hey, I'm going to treat privacy as a game. IRBs aren't always amenable to that. Along the way of doing this research, we hit what should have been obvious to us, which was that there are situations in which clearly the situation is risky, but it's a no attack result, in that the defender is sufficiently deterred because the expected value of the payout is negative, that they're never going to play. So we were really interested in where this would happen. So here's my result is better than your result graph, but I want to show you this because it's really quite fascinating in terms of what happens. So here's this safe harbor policy. What you see is that the publisher gets the payout, They induce a bit of a negative externality in that the attacker will be successful in a couple of cases, but that's the overall payout. Okay, so if you play out the Stackelberg game that I showed you before, it shows up right in this region, in that the publisher, if what you're interested in doing is maximizing the total amount of payout, then what it suggests is that you should be willing to tolerate a little bit more collateral damage in terms of the amount of payout that would go to the attacker. Now, obviously, they're not always going to get paid this amount. It's just how much more risk are we inducing? If you wanted to play out a safe harbor friendly model, you can get a little bit less payout, but you can end up in a situation where you have like almost no payout going to the attacker. That's great to know. In other words, if somebody tries to share the maximum amount that a simple federal policy tells them they can use, they may be unnecessarily putting more risk in the system than they need to. Now, the no attack situation, in this situation, the attacker gets zero benefit, but the publisher gets a substantial amount of benefit. So what happened here? Turns out that in these types of policies, what we ended up having was that instead of sharing patient level data on a annual, their age on a 1 year window, we were just putting people into 2 and 3 year age bins. And that sufficiently made it difficult, or made people look sufficiently similar, that it was too difficult for an attacker to make a claim of correctness in their identification. And that this was different than what the simple federal policy was telling people that they could do. But we said, if you're allowed to go and do an alternative way of sharing, which is permissible under the regulation, then you have these options that are really going to benefit everybody a lot more than what you currently do. So if you're interested in playing around with this type of an approach, we worked with a team at Technical University of Munich to integrate it into an open source anonymization toolkit known as ARX. So feel free to play around if you're interested. Now, what I wanted to show was how we've taken these principles and put them into practice and what you can actually do with the data as an artifact. So one example is I've done some work with a couple of pharmaceutical companies who are sharing clinical trials data as a requirement under the European Medicines Agency's policy. They have to share this data to this this repository that has been established. But this principle started, or this concept started with something known as Project DataSphere, which was started by Sanofi Aventis to share data on failed phase 3 clinical trials, particularly oncology trials. And so when that data started to go out the door, where we could give some provable bounds on what you could and couldn't do in terms of penetration, we found that if you give people sufficient incentives, they can actually do really interesting new things with them. One of which is that the Dream Challenge program, they created a prostate cancer challenge. And what people started finding was that when you looked across clinical trials, you could actually look at the natural etiology of prostate cancer on a scale that had actually not been done before. And so this type of data, once we started putting it out the door, enabled studies that in the public domain where we felt pretty comfortable that the data was not going to be subject to attack. We've been doing this now for about 8 years and haven't had any type of problem. Okay, I still got a little bit of time, so let me give you another example. What I showed you just now was demographic data sharing, but you could also envision a situation in which you have other types of data. So genomic data was the other example I gave you. And so the Sphinx program, you can read what it is there. It's an artifact of the NIH's Electronic Medical Records and Genomics Network. This is an environment where they're trying to share data on single nucleotide polymorphism rates with respect to this population. So we have now, at the time when we did the study, there were about 8,000 people that were in Sphinx. They were looking to publish 2,500 single nucleotide polymorphisms, over 38,000 genomic variant regions, right? 51,000 distinct SNPs here. In this situation, we found that it was about $45,000 that was going to be going to the publisher. Around, at the time, it was about $360 for a successful detection and about $180 to access this type of data. Now, we assumed that adversaries would be a little more tolerant of incorrect matches, so we allowed for a 10% false positive rate and required a 50% true positive rate in the claim. And then we also assumed that there was a prior probability of somebody being in the data set of 5%. And that's something I haven't really talked about here, because the prior probability of somebody being in a data set is actually really quite critical to supporting any type of a claim. Okay, so this is a slightly different view of the type of graph I showed you before. This isn't the payout. What you're seeing here on the x-axis is the utility that somebody would receive for sharing data, and the y-axis is the privacy. So you want to be in the upper right-hand corner. That would give you the ideal solution. You've maximized utility and you've maximized privacy. I call it ideal because it's impossible to achieve. Now, if you were to just share the genomic data, you don't remove anything, then the rate at which people would be successful in claiming that somebody was a member of this cohort would be on the order of around 40%, okay? Now, we took a look at the approach that Bustamante's group that I mentioned earlier had recommended for the publication of this type of data, and that's what you see in this red circle. Basically, it says you have all these options in terms of how much of the data do you want to hide, right? And they said, you know, right about here is where you should let the data go out the door. You could continue to remove information, but they thought that that was unnecessary. However, this assumed that the only protection that you could institute in place would be hide snips. So we said, well, what happens if you further deter somebody by saying that they're going to have to pay for the violation of like a data use agreement? Could you specify liquidated damages such that they know upfront how much they would end up losing in the event that they make a claim that gets detected? And so what we found is that this is one of the reasons probably why most organizations don't manipulate the data and that they just assign data use agreements, because they really do scare people into being relatively good actors, or at least the theory suggests that they should. But what we've also found is that you can do better by combining the data use agreement with a minor amount of data manipulation. It creates enough uncertainty with respect to the data that even if they're not scared away by the data use agreement, they may be scared away by the fact that the data doesn't have sufficient detail for them to be correct in any claim they make. So I've got a couple minutes, I believe. So I wanted to focus on one of the tricky aspects of this problem, is that what you get is when you're trying to protect privacy using these types of strategies, which are really just variations on de-identification methods, they tend to create scenarios that lead to the hiding of small populations, as you would expect. So what this means is that you're going to lose your ability to do research on certain types of populations. So we've run into this problem with the all of us environment, for instance. Like, we don't have that many people who are transgender, so we hide the data, and we get criticized because we're not allowing research to be done on that population. Not many Pacific Islanders in your data, hide the data. Not many people from the rural environment, you hide the data. So in other words, what this basically means is that you get to share data when you have populations of sufficient size. Why is this a problem? I inverted the privacy utility axis here, but what I was alluding to earlier was that it's a privacy utility trade-off. And so we think of it as there's a continuum along which we can parameterize or we can optimize. But this is, you really have to think about this in terms of there are multiple groups that you're doing this for. And so you have majority populations, you'll have minority populations, and then you'll have super minority populations, right? Where choose race as an example. Most majority populations, it will be a Caucasian group, minority might be the Black and African American group, and super minority might be a Native American population, right? And so the trade-off is such that in order to get to the same level of privacy, you have to force them down into lower levels of utility. But in reality, it may actually be the case that they didn't even have complete utility because there wasn't sufficient information there to begin with. And so the trade-off may actually be even worse for these populations. And so if you induce a uniform privacy requirement across all of these populations simultaneously, then where you end up finding your optimal point or your maximal operating point is it ends up forcing you into the situation of unfair or unequal allocation of the ability to have your data studied for these groups. So this brings up the question of algorithmic fairness, or what we're calling in this situation data fairness, right? So regardless of how you go about manipulating data, if you end up in situations where you're going to amend the minority more than the majority, then this perpetuates the problem of continuing to learn more from the majority population. You will learn better policies for the majority population. And this is really what you would call the rich getting richer. So you can imagine the induction of fairness in this situation in some really interesting ways that might seem counterintuitive. One of which might be that if you know that the majority population is going to gain better detail than a minority population, then maybe what you should be doing is putting them all at the same level of detail and say, well, I can't share race for the majority group if I can't share it for the minority group. And that might be considered a way of putting in some type of balance. But is that really where we want to go as a society? That's an open question. Okay, so where are we heading? So what I just showed you is that there are problems with the standard approach to de-identification. And so where we've been working over the last couple of years is really in the hardcore AI of getting into synthetic data generation. And what we've been doing is using generative adversarial networks to learn profiles of clinical profiles, as well as demographic characteristics of patients, and then simulating records, both in a static sense, like the sets of diagnoses that they have, as well as what those diagnoses look like over time. And so this is my graph is better than your graph, but basically what you see on this x-axis is how well you're preserving the ability to do classification on, or it's precision and recall with respect to predicting a diagnosis code for somebody in the original data versus on the y-axis what you get in the simulated data. And so we've kind of pushed the technology to the point where it's starting to look like what you would get after two random samples out of the original data, but I don't have much time to go through this today. The other way that people are starting to think about sharing data is as I alluded to at the very beginning, which is that maybe if the trust issue can't be resolved, then where that ends up putting you is back into the notion of secure enclaves. But it may be that you can do this over multiple institutions simultaneously so that you can use them for validation and model checking. So I can learn a model at one location and then test it at another location to see if the model is actually generalizable, which would be better than just doing it all at one location where you're subject to the biases that come into play simply by it being an artifact of a single data collection. We recently demonstrated how you could do this with Jean-Louis Raisaro's group on sharing distributed COVID-19 data. Okay, so let me close out because I wanted to leave a couple minutes for questions, and wanted to give you like some concerns about what I worry about, because even though I wanted to talk a little bit about AI and privacy, there's the bigger world out there, and so what we're dealing with now is that as the sheer number and the diversity of what I call investigators, but you might call them researchers or data users, as that grows, it makes it really difficult to understand incentive structures. It makes sense when you understand if you're giving controlled access to a researcher at an academic institution. Things start to get a little bit weird if you have a request from a high school student in the middle of Finland. The data is becoming increasingly more detailed and complex. we believe that our methods will scale to a certain degree. We can do this for upwards of like around 10,000 to 20,000 variables, as I showed with respect to the genomic data. But where data sets are starting to head with the multimodal nature of getting electronic medical records, plus genomics data, plus imaging data, plus social determinants of health, the amount of data just may become too detailed to the point where the notion of de-identification just is not feasible for sharing that level of detail. So this notion of risk analysis and intelligently select policies, it has potential. But even if you do find a situation in which you want to use it, you need to have people agree upon what's an appropriate adversarial model and what's an acceptable level of risk that we're willing to tolerate. And that's a really hard conversation for people to have, because when you talk with people who are data managers, and particularly when you talk with the lawyers who are trying to watch out for the best interests of an organization, they really, really, really are risk averse. And the notion of any amount of risk is very difficult to tolerate. So even though I showed you an example before where I said, okay, there's no attack, this assumed that the adversary would get benefit of X dollars. But what happens if we were wrong and they really see a benefit of X times 1,000? We've done a number of sensitivity analyses, which is why when we make recommendations, we don't rely on a single estimate. We rely on how close or how far away from that type of precipice do we live. The other thing is that breaches are inevitable. They will happen, and one of the reasons why organizations are freaking out is that like they don't know how to respond. And so even if you have a single record that gets re-identified or a single record that gets compromised, which is a horrible thing, it doesn't mean that the entire resource has been broken. But the problem is that organizations tend to respond in a non-probabilistic manner. It's either broken or it's not broken. And so this lack of probabilistic reasoning is really hurting everybody. So there needs to be a mindset change in terms of acknowledging that there are risks, but we've done our best to mitigate them. I could have shown you an attack that took place where one individual out of 1 million was actually identified, and the organization that shared the data acknowledged that they were negligent, such that they ended up paying out as if they had actually had 1 million people breached, which doesn't really help anybody. Okay, so that's my closure. There's a lot of people who work in my group or have worked in my group, and we work with a lot of people across the country, and I'm just going to give them a little bit of a shout out here and say that it's been really fascinating working with places like Emerge and the All of Us program. And I'll stop there.
Thanks so much, Brad. That was a really interesting talk. I've seen some talks about privacy, and every time I always get a little bit paranoid. So I'm glad that you guys are working on this and thinking about it when we're not.
Think about it when I sleep.
So we do have already one question. There might be some more pouring in. Since I will let you leave your slides up, I'll go ahead and read it to you.
Sure.
Could you share your thoughts on federated learning? You touched on it toward the end, I think.
Yeah. So federated learning, the funny thing about federated learning is that it's actually been around for probably about 30 years. We just haven't really automated it to the degree that we're now starting to do so. The challenge with federated learning is that you really have to be careful about when you choose to combine data. It's not so much a privacy problem, it's really a statistical modeling problem. I think the example I can offer is that errors or biases within a single data set may end up influencing other data sets. So if you have one site, for instance, that has a lot of bias, and then you try to pool all of the results, like you're trying to aggregate across all of the results, then you may end up being subject to the biases of the organization that contributed the largest amount of data. And to try to mitigate that effect, instead of trying to do federated learning off of the individual level records, what may actually be a better approach is to acknowledge that you should do things like meta-analysis in a secure manner. And so that way you can allow the biased effects of each location with like cases and controls to cancel each other out locally, so that they don't end up getting into a propagation situation with respect to the other organization's data. So I think, this is why I say I think federated learning it has potential. I think that it's going to be useful when an organization doesn't need to disclose individual level records, but it doesn't necessarily do away with the problems of statistical bias.
So no other questions so far, so I'll go ahead and ask one. So you were kind of talking about with a super minority and the privacy versus utility. So coming from a stats background, it's very hard to study very small data sets if you're trying to do statistics. And so you were
Yeah.
thinking about using synthetic data to kind of help with the privacy. Have you thought about that in terms of boosting the size of a super minority type of data set so that you'd actually be able to study it statistically?
Yep, it's exactly what we're doing right now. We're doing it, so synthetic data generation is useful in two situations. One is the completion of the creation of a completely new data set. The second is in terms of augmentation, where you learn a model and then you supplement with simulated data. And it turns out that that's actually really useful for if you have a little bit of a signal, then if you can learn enough of the model, then the simulation of the data in that scenario gives you the ability to learn a classifier that has more confidence than what you would have had earlier. But I would say that you're never going to be able to generate synthetic data for like not n of 1, but like n of 5, n of 10 cases, because you're never going to have the ability to build a sufficiently learned model. It's going to be so underspecified that the confidence bounds on whatever you generate is going to be too wide to really rely on anything. So
Okay.
I think synthetic data, it's going to work really well for data where you've got majority populations and people are uncomfortable disclosing that information. And it will be really useful for supplementing data from a learning perspective, but I don't think it's going to be really a complete privacy protection. I say that because what happens is that if you have a minority population and you have a mixture of the real data and the synthetic data, and it's not possible to tell the difference between the real data and the synthetic data, then that will actually work as a privacy protection mechanism. So it will depend on how well your synthetic data generator works in its augmentation strategy, because if it's generating things that you haven't seen before, it may not be so useful, but if it's generating things that are sufficiently similar to the original data, it will work from a privacy protection method. So the answer is it has potential.
Okay. That's really interesting.
Yeah, it's a completely open area right now. Like synthetic data generation it's been done for decades, but in the context of high dimensional data, it really has only been explored with medical records for about 4 or 5 years now.
It feels a little bit like bootstrapping, but of course it's more complicated and you're actually relying on the modeling itself and that being fitted. So it's a little bit more complicated and probably
It's
harder with very small data sets.
it's like bootstrapping, only it's probably another way to explain it would be it's more like a latent model learner,
Okay.
in that you're not going to sample off of the records themselves, but instead you're going to learn a model based on those records, and then you're going to simulate based on the learned model. So you have the potential to simulate the original records, but it's more of a smooth representation of a distribution over those records, and you're going to sample from the distribution, even though you
Okay.
may not have seen something.
Okay. Got it. Very cool. I think we're getting a lot of people slowly peeling off since we're
Sure.
right a little bit past 3 o'clock. And I think we hit all of the questions in the Q&A box. So I guess we can go
Good
ahead and
deal.
wrap up.
All right.
So yeah, thank you very much for coming to speak with us. I know that Mike had some potential contacts that he wanted to make sure that you got in touch with. So you
Mhm.
might be looking for a couple of emails. And
Sounds
similarly,
good.
anyone in the audience, feel free to get in touch.
All right. Thanks for the invite.
Thank you so much.
All right. Talk to you guys later.
Thank you,
Bye,
Brad.
everyone.